Hi all, now we will discuss another remaining part of theorem 6.12. So this is the C part. If f belongs to R alpha on AB, then f belongs to R alpha on AC and f belongs to R alpha on CB. Which are AB in the interval. If you insert a point, then you can get f is integrable over this interval, and f is also integrable on this CB. Okay. So in order to prove this, we start with our first assumption is f belongs to R alpha. Then for every epsilon greater than 0 there exists P such that P belongs to P of AB such that UP F alpha minus LP F alpha is less than epsilon. So this is the characterization. Now you define a partition P star by inserting C, a particular point inside this. Now we have the inequalities. If you consider the upper sum corresponding to this P star refinement of alpha, we can write it as less than, okay, less than or equal to UP F alpha. We already proved this. Similarly, if you take the lower sums, you can get less than or equal to the lower sum of the refinement will be greater, okay, P star F alpha. That means if you take the refinement, then lower sum increases and upper sum decreases. This is the idea. Now you write this LP F alpha is less than or equal to LP star F alpha. We know that LP star F alpha is this P star is P union C. Okay, so if we have partitions like this, we inserted a point C over here, and we have other points here. So we can write this P star as partition of AC plus partition of CB. Okay, so you can get two partitions, P1 and P2. So this P star can be considered as P1 union P2, where P1 belongs to P of AC and P2 belongs to P of CB. Okay, you can split this P star in this manner. So that will be written as, this P star can be written as LP star F alpha can be written as P1 F alpha plus P2 F alpha. Okay, where P1 and P2 satisfies this condition. Now we know that this is less than or equal to U P1 F alpha plus U P2 F alpha. Okay, because lower sum is always less than or equal to upper sum, but this is the upper sum corresponding to P star F alpha. But we know that when we take the refinement, upper sum decreases, so this is less than or equal to UP F alpha. Okay, so this is the case. Now we have this inequality. Here we have LP F alpha, and this is our LP1 F alpha plus LP2 F alpha, and here we have UP1 F alpha plus UP2 F alpha, and here we have UP F alpha. So we know that the difference between these two quantities is always less than or equal to difference between this and this. Okay, now you can write from these inequalities, you can write this quantity minus this is always less than or equal to. Okay, so we write UP1 F alpha plus P2 F alpha minus LP1 F alpha minus LP2 F alpha is less than or equal to UP F alpha minus LP F alpha. Okay, but we know that UP F alpha minus LP F alpha is less than epsilon, so this is less than epsilon. That is, if we consider UP1 F alpha minus LP1 F alpha plus UP2 F alpha minus LP2 F alpha. So this is less than epsilon, but we know that these two quantities are non-negative quantities, so both will be less than epsilon. So this implies UP1 F alpha minus LP1 F alpha is less than epsilon, and u p2 f alpha minus l p2 f alpha less than epsilon. Okay, this shows that since p1 is the partition of AC, then f belongs to R alpha on AC and f belongs to R alpha on CB. Okay, because P2 is the partition of CB. Now we'll prove the the inequality involving integrals. Okay, so first we have this result, this UP1 alpha, UP1 f alpha plus UP2 f alpha is less than or equal to 0. So we start with that. So UP1 f alpha plus, or we can start it the other way, we write it as, that is the easiest way. So we start with LP, here we have LP f alpha is less than or equal to this, LP f alpha is less than or equal to LP1 f alpha plus LP2 f alpha. Okay, we start with an arbitrary partition of this AB. Okay, now you have from that partition you can get two partitions, P1 and P2, such that P1 is a partition of AC and P2 is a partition of CB, and we've already proved that this f belongs to R alpha on AC and f belongs to R alpha on AB. So we can replace this by less than or equal to supremum of LP1 f alpha. Supremum of LP1 f alpha is same as integral A to C f d alpha, plus this can be replaced by the corresponding supremum, then that will be integral C to B, because P2 is the partition of CB, integral C to B f d alpha. Okay, now take the supremum of supremum P varies over partition of AB, LP f alpha, so that will be integral A to B f d alpha less than or equal to integral A to C f d alpha plus integral A to C to B f d alpha. Okay, so this is our equation number 1, and now we will prove the other inequality as well, then we can get the additive property of the integral. So now we will prove the reverse inequality, that is obtained by replacing this f to minus f. Okay, if you replace this by f by minus f, you can get, this is true for every f, so if you replace this by minus f, you can get integral A to B minus f d alpha less than or equal to integral A to C minus f d alpha plus integral C to B minus this is integral C to B minus f d alpha. Okay, now taking minus out and cancel each other using the previous part, then you can get integral A to B f d alpha is greater than or equal to integral A to C f d alpha plus integral C to B f d alpha. Okay, by cancelling minus sign, then reverse inequality will be reversed. So this is our second inequality. From 1 and 2 you can get, from 1 and 2 we have integral A to B f d alpha equal to integral A to C f d alpha plus integral C to B f d alpha. Okay, so this proves C part. Okay, now we have D part. What is the D part? D part says that if f belongs to R alpha on AB and mod f of x is always less than or equal to capital M. If you are given a bound for this f of x on AB, then you have an estimate for this integral A to B f d alpha. So this modulus will be always less than or equal to m times alpha of b minus alpha of a. Okay, so this is because we know that the upper sum, if you consider the upper sum or lower sum, anything that will be written as, you write mod f of x is always less than or equal to m. So this implies minus m less than or equal to f of x less than or equal to m. By taking integral over this inequalities, we have integral A to B minus m, this is a constant d alpha less than or equal to integral a to b f d alpha less than or equal to integral a to b this m d alpha. Okay, we already proved that f1 is less than or equal to f2 implies integral f1 d alpha is less than or equal to integral f2 d alpha in the second part. So we have this result, and we can take this minus m out. Integral a to b 1 d alpha less than or equal to integral a to b f d alpha less than or equal to m times integral a to b 1 d alpha again. But we know that integral a to b 1 d alpha, okay, so this is nothing but alpha of b minus alpha of a. Okay, because in this case our f of x equal to 1, the corresponding up f alpha will be, the maximal is always 1, so that will be same as summation I equal to 1 to n 1 times delta alpha I. So this is delta alpha I, so this will be alpha of b minus alpha of a. Now you have taking infimum on both sides, you can get infimum of this is same as infimum of this, and infimum this is nothing but integral a to b f d alpha, that is 1 d alpha. If f of x equal to 1 here, 1 d alpha, that will be alpha of minus alpha of a. Now we have this is minus m times alpha of b minus alpha of a less than or equal to integral a to b f d alpha less than or equal to m times alpha of b minus alpha of a. So this proves, or this implies, modulus of integral a to b f d alpha is always less than or equal to this m times alpha of b minus alpha of a. So this proves d part as well. Now we have the last part, e part. E part says that if f belongs to R alpha 1 and f belongs to R alpha 2, we have two monotonically increasing functions alpha 1 and alpha 2, then clearly f belongs to R of alpha 1 plus alpha 2, okay, and the corresponding integral, and integral a to b f d alpha 1 plus alpha 2 can be considered as integral a to b f d alpha 1 plus integral a to b f d alpha 2. The similar fashion, if we take f belongs to R alpha and c is a positive constant, then f belongs to R c alpha. C is positive here because otherwise this c alpha will not be a monotonically increasing. If alpha is increasing, c is positive, then c alpha is also increasing function. Okay, so we will prove that f belongs to R of c alpha, and we can compare integral a to b f d c alpha will be same as c times integral a to b f d alpha. Okay, we will prove this part. So this is the last part of this theorem 6.12. Okay, we set alpha is equal to alpha 1 plus alpha 2 to prove this. Now we know that alpha of some xi, alpha xi will be alpha 1 of xi plus alpha 2 of xi, and alpha of xi minus 1, that will be alpha 1 of xi minus 1 plus alpha 2 of xi minus 1. By taking the difference between these two, then this will be delta alpha I, and this will be delta alpha I. This can be written as alpha 1 of xi minus alpha 1 of xi minus 1, that will be delta alpha 1 I plus this will be delta alpha 2 I. Okay, so delta alpha I can be written as this form. Now in order to prove this f belongs to R alpha 1 and f belongs to R alpha 2, we have first we our assumption is if f belongs to R alpha 1 and f belongs to alpha 2, then corresponding to this f1 this alpha 1 and alpha 2, we have for every epsilon greater than 0 there exists a partition p1 such that p1 belongs to p of ab such that UPF alpha 1 minus LPF alpha 1 less than epsilon. Similarly, you can get for the same epsilon P2 belongs to P of AB such that UP f alpha 2 minus L p f alpha 2 less than epsilon. And now you take the common refinement of this p1 and p2, say p1 union p2, you can get the same thing, f alpha 1 minus LP f alpha 1 less than epsilon, and up f alpha 2 and up f alpha 2 less than epsilon, because if you take the refinement both will hold. Okay, now you can see we need to prove that this up f alpha, okay, minus LP f alpha. Okay, so this will be this is equal to by the definition you can write it as summation I equal to 1 to n capital Mi minus small mi times delta alpha I. Okay, by definition this is the UPF f alpha minus LPF alpha, and this can be written as I equal to 1 to n this capital Mi minus small mi times this delta alpha I can be written as delta alpha 1 I plus delta alpha 2 I. Okay, now you distribute this bracket, so you can get summation I equal to 1 to n capital Mi minus small mi times delta alpha 1 I plus the summation I equal to 1 to n capital Mi minus small mi times delta alpha 2I. Okay, now this is nothing but up f alpha 1 plus minus LP f alpha 1, that is this one. Similarly, this can be written as up f alpha 2 minus LP f alpha 2. But we know that we are given that f belongs to R alpha 1, so this can be made less than epsilon, plus this is also less than epsilon. We know that these two quantities are less than epsilon, so we have this is epsilon plus epsilon, that is 2 epsilon. So this implies f belongs to R of alpha 1 plus alpha 2. Okay, so this proves the first part, and now we will give the relation between corresponding integrals. Okay, so first we have this result up f alpha minus LP f alpha, that is equal to this up f alpha 1 minus this plus this one. Okay, so we prove the integral, the relation between the integrals. For that we consider LP f alpha can be written as this is same as LP f alpha 1 plus LP f alpha 2. Okay, this is because summation I equal to 1 to n small mi delta alpha I can be written as summation small mi delta alpha 1 I plus summation small mi delta alpha 2I. You can write delta alpha I as delta alpha 1I plus delta alpha 2I. Now you replace this by this is less than or equal to by taking if you replace this by its corresponding supremum, this will be integral A to bf d alpha 1 plus, you can replace this also related to bf d alpha 2. Okay, now we have LPF f alpha is less than or equal to this by taking the this is true for an arbitrary partition, P belongs to AB, P of AB. Now taking the supremum on both sides, you can get integral A to B f d alpha is less than or equal to this. We put it as equation number 1. Now you write up f alpha 1 plus up f alpha 2 is equal to up f alpha. Okay, that is because if you replace small mi by capital Mi in this equation, you can get this one. Okay, but we know that this is always greater than or equal to integral A to B f d alpha 1 plus integral A to B f d alpha 2. Now take the infimum on both sides. Okay, so that that will be integral A to B f d alpha 1 plus integral A to B f d alpha 2 is less than or equal to the infimum of this, that is integral A to B f d alpha. Okay, this is equation number 2. So 1 and 2 implies integral a to b f d alpha is same as integral a to b f d alpha 1 plus integral a to b f d alpha 2. Okay, so this proves the first part. Now we have the last case. If f belongs to R alpha, then we'll prove that f belongs to R C alpha, okay, where C is positive. In this case, we write alpha of this alpha of xi is C times alpha of xi is same as C alpha of xi is same as C times alpha of xi. Okay, so this implies delta C alpha I is same as C times delta alpha I. So this is the relation between these two. We write this is Ci, write it as C alpha I. C alpha I, delta C alpha I is equal to C times delta alpha I. Now we have UP f C alpha is same as C times UP f alpha. Okay, and similarly LP f C alpha equal to C times LP f alpha. Okay, from these two you can write UP f C alpha minus LP f C alpha is same as C times UP f alpha minus LP f alpha. Okay, which is if we assume this, if f belongs to R alpha, you can get for every epsilon greater than 0 there exists a partition with this quantity is less than epsilon. Okay, now we have this is less than C times epsilon. Okay, so this proves f belongs to R of C alpha. Okay, now we can get the relation between the integrals of these two. Okay, integral of f alpha and integral of f d alpha and integral of f d c alpha. Okay, to compare this, we write this relation UP f C alpha is same as C times UP f alpha. Now take the infimum on both sides. Infimum UP f C alpha equal to C times infimum of UP f alpha. Since the C is greater than 0, this will be equal. Now this we have left side is integral of f d C alpha, and that will be same as C times, this will be integral of integral to be f d alpha. So this proves the relation between the integrals. Okay, so with this we can prove all the 5 properties of integrals as Riemann-Schiller's integrals given in 6.12. Okay, in the next class we will discuss theorem 6.13.